So today we discuss the second part of the higher order homogeneous equation with constant coefficient. Okay, so in this section we will discuss the higher order starting with the third order, fourth order and so on. Okay, and this higher order homogeneous equation also the equation with constant coefficient. And the method that we will use here is actually same as what we did discuss in the 4.3 part 1. Okay, it's actually using auxiliary equation and using the solution in terms of the exponential form. Okay, so let's see the formulation first. Okay, so this is on the general solution for the homogeneous linear n order differential equation. Okay, so let's see you are given the n order. Okay, in general you are given the n order linear differential equation homogeneous equal to 0. Okay, so by using the same standard procedure as the previous topic in 4.3 part 1. Okay, so to solve this we use the solution in terms of the exponential form. Okay, so therefore the corresponding auxiliary equation, okay, for this n order differential equation is given by this polynomial equation of degree n. Okay, so you can see from here the en, the coefficient en. Okay, this one is the n derivative. We can replace this by the m to the power of n. Okay, and this one is the same here, coefficient, and the n minus 1 derivative replaced by m to the power of n minus 1. Okay, and we have the second derivative replaced by m square, the first derivative replaced by m, and if there is no derivative means that no m. Okay, so from here you can see that the corresponding auxiliary equation is actually a polynomial equation of degree n. Okay, unlike in the 4.3 part 1 when we discussed the second order linear equation homogeneous, the corresponding auxiliary equation is in terms of quadratic equation because the highest degree is m. The degree for the equation is the second degree. Okay, but here since that is in terms of the n order, so means that the degree for this polynomial equation is degree n. Okay, so the way how to solve this auxiliary equation is actually same as the previous topic. It's just like the challenge is that you have to find the n root for this equation. Okay, so you can solve this using factoring method. Okay, and if you want to use your calculator, I think the calculator only limited until fourth order or maybe the third degree or the fourth degree. Okay, so you cannot depends on the calculator to get the n root from this equation. So you have to at least know how to use the factorization to find the root m. Okay, so based on that, let's see you have n distinct real root. Okay, so let's see after you solve this polynomial equation, you get n different roots. Okay, so therefore you will get n different solution here. Okay, starting with the first solution, y1 is e to the power of the first root. Okay, m1 times x. Okay, the second solution is e to the power of the second root, okay, multiplied by x, until you have the n solution, yn equal to e to the power of the n root, okay, here, put here, and then multiply by x. Okay, so you will get n corresponding solution, okay, from this after you solve the auxiliary equation, okay, with the n distinct real roots. Okay, so after you get the y1 until yn, then the general solution for this equation is given by y equal to c1 y1 plus c2 y2 until cn yn, because based on the previous topic, okay, once you get the corresponding solution, the corresponding solution here are confirmed linearly independent. So based on the theorem 4.1, we can combine the solution as c1 y1 plus c2 y2 until cn yn. Okay, so this is the solution for the n order linear differential equation with constant coefficient. Okay, where the number of roots here are n distinct real roots. Okay, so let's see the example here. Okay, now let's see for the first example. Let's see, okay, because I will try to explain to you how to write the formulation first. Okay, so let's see you are given the roots, okay, for the auxiliary corresponding auxiliary equation are this. Okay, so let's see you are given the root are 1 2 3 4 5 roots. Okay, and the roots are all different roots. Okay, distinct real root 1 2 -1 4 and 5. Okay, so based on this, since that all these are different roots, means that you will get a 5 different solution because you have 5 different roots here. So the corresponding solution will be, for the first root will be y1 equal to e to the power of x. So you put the value of this root, okay, on the exponential form, because the formula for exponential is e to the power of mx, okay. So you put a 1 here on x, okay, so you get y1. And the second root, you get y2, the corresponding solution, e to the power of 2x, okay. The third root is e to the power of negative x for this root, okay. And the fourth root is 4, then you get the fourth corresponding solution, e to the power of 4x. And the last one is the fifth root, which is 5 here, you get the fifth corresponding solution, e to the power of 5x, okay. So we have y1 until y5, okay. Then according to the theorem, okay, all these are linearly independent. So therefore we can write all this in one solution, y, okay, equal to c1 y1 until c5 y5, okay. So the final answer for this the general solution here will be y equal to c1 e to the power of x, okay, from y1 here, and then you have c2 e to the power of 2x until c5 e to the power of 5x, okay. So this example show you how to write the corresponding solution and how to write the final answer, the general solution, okay, if you are given 5, if you are given 5 distinct real roots like this, okay. Okay, now, so let's see the next, okay, the next formulation here is for the repeated real roots, okay. So here again, okay, for the n order differential equation with constant coefficient, okay, given by this equation, okay. So n order here. So the first, the first step is to write down the corresponding auxiliary equation, okay. So based on this equation, the corresponding auxiliary equation is given by this polynomial equation of degree n, okay, equal to 0, okay. So now from this, let's see, after you solve this polynomial equation, you get n repeated real roots, okay. Means that your first root until the last root, the n root, all the same root, okay. So you get n repeated real roots, okay. So what happened is that the first solution, the first corresponding solution, okay, actually is e to the power of mx, okay. So let's see, all the roots, okay, are same root, and that root is equal to m. So the first solution is e to the power of mx, okay. But the second solution until the last solution, okay, you cannot write the same solution here because it's the same root, okay. So what happened here is to avoid a duplication with the y1, okay. The y2 you have to multiply by x, okay. The x e to the power of mx, okay. And the y3, to avoid duplication with the y1 and y2, you have to multiply this by x squared, okay. And you have to do that all, okay, for until the last solution yn, okay, is equal to x to the power of n minus 1 e to the power of mx, okay. So make sure that the second solution, starting with the second solution until the last solution, okay, make sure no duplication with the previous solution, okay. So after you get the y1 until yn, so therefore the general solution for this equation is given by c1 y1 plus c2 y2 until cn yn, okay. So this is the solution for the n order equation with constant coefficient if you obtain the n repeated roots, okay, from the auxiliary equation, okay. Okay, let's see example. Okay, let's see, you are given here, let's see, you get, after you solve the auxiliary equation, you get 1, 2, 3, 4, 5 roots, okay. But all the 5 roots are repeated root, the same root, okay, 2, 2, 2, 2, okay. So what happened here, the corresponding solution, okay, for the first root is, okay, you just put into the exponential form, e to the power of 2x, okay. However, the second root, you cannot also put e to the power of 2x, otherwise it's a duplication with the y1. So the second root, okay, since that is repeated with the y1, so you have to multiply by x for the second solution, okay. And the third solution also, okay, since that is repeated with the y1 and y2, so the y3 you have to multiply by x squared, okay. And then the fourth solution also duplicate with the y1, y2, y3, then you have to multiply by x to the power of 3. And the last one, okay, the fifth solution, you have to multiply by x to the power of 4, okay. So you can see that each one of these solution y1 until y5, there is no duplication. So make sure that all these not duplicate, okay, all different solution, okay. Okay, even though that, okay, you have the all repeated real roots, okay. So based on this, after you get y1 and y5, then we can combine all these, since that all these are linearly independent solution. Then we have the general solution is y equal to c1 e to the power of 2x until the last one c5 x to the power of 4 e to the power of 2x. Okay. So now we consider an example where you have to solve the polynomial equation of the auxiliary equation. Okay, so given the n order linear homogeneous differential equation. Okay, so the first example here is actually for example that involve real, distinct, and repeated roots. So it's combination of the real, distinct, and repeated roots. Okay. So for the previous example, you are given the m. So but now for this example, you are given the homogeneous equation with constant coefficient. You need to find the corresponding auxiliary equation, and after that you need to solve that equation to find the m. Okay, so basically you have to find the general solution for this equation. So this is the third order linear differential equation, homogeneous, equal to 0. Okay, so first of all, to solve this, we need to start with the auxiliary equation, the corresponding auxiliary equation. So from here, the corresponding auxiliary equation for this third order linear homogeneous equation is given by this. You can see that this is the third derivative replaced by m to the power of 3. And then this one coefficient is still the same, -3. And then this one second derivative replaced by m square. And first derivative replaced by m. And the last one, since that no derivative, no m, means that here is only 27. Okay, so actually there is m here, but the m here is to the power of 0. So m to the power of 0 is equal to 1. Okay, so this is the corresponding auxiliary equation for this third order linear homogeneous equation with constant coefficient. Okay, so you can see that this is a polynomial of degree 3. Okay, so we can solve this polynomial of degree 3 using factoring method, or you can also solve using your calculator to get the m root. Okay, so now for this third order polynomial equation, you must obtain 3 roots. Okay, so the roots can be repeated, can be distinct, can be a complex root. Okay, so what are the roots here? Okay, now after you solve this, since that I didn't show anything here, means that I'm using my calculator. Okay, so for this equation, okay, the number of roots, there are 3 roots here, all 2 repeated, 1 distinct. Okay, so we have 3, 3, and -3. So make sure if you use your calculator, okay, make sure you get the same root as this. Okay, so be careful, your calculator sometimes for the repeated root, or they can only display once only. So you have to know which one is repeated. Is it 3 or -3? -3. Okay. So in this case, I think but better for you to use the factoring method to identify which one is repeated, 3 or -3. Okay. Okay. Now, so for these roots here, there are 3 corresponding equation, y1 until y3. So the first 2 equation here involve the repeated root 3. So now we have y1 equal to e to the power of 3x. Okay, and the second one, since that repeated also with the with the first one, so y1 we have to y2 we have to multiply by x e to the power of 3x. Otherwise, if you didn't multiply by x, then you'll get the same for y1 and y2. Okay, and then the y3, since that is not repeated with the first and the second, so you just plug in into the formula e to the power of mx. So you get e to the power of -3x. So this is for y1 until y3. So therefore, okay, now the general solution for this equation is given by c1 y1 until c3 y3. So the final answer for this equation is y equal to c1 e to the power of 3x plus c2 x e to the power of 3x plus c3 e to the power of -3x. Okay, so this is the general solution for this equation given by example 1. Okay, now for the example 2, this is the example that show you when you solve the auxiliary equation, you will get a combination of the real and repeated roots also. Okay, so let's see, you have this equation. Find the general solution for this given homogeneous equation. So you are given 5th order. Okay, a linear homogeneous equation, because the highest highest derivative here is the 5th derivative. Okay, homogeneous because it's equal to 0. So how to solve this? Okay, first you need to write the corresponding auxiliary equation for this homogeneous equation. So based on this, the corresponding auxiliary equation will be for the 5th derivative replaced by m to the power 5, and the 4th derivative m to the power 4. This one is the 3rd derivative m to the power 3. So the coefficient 5 and 6 we just take from here. Then you get a polynomial equation of degree 5. Okay. Okay, this one I think you cannot solve this using your calculator. So you have to know some technique of the factorization for this. Okay. So we use the basic technique of the factorization by factoring out the common factor. This one I can factor out m to the power of 3. So here m to the power of 3. Factor out m to the power of 3. Then the remaining will be m squared plus 5m plus 6 equal to 0. So this one will be a quadratic equation. And this is the cubic equation m to the power of 3. So solve each one of these equal to 0, m cubed equal to 0. Since that is the power here indicate that there are 3 zeros here for m, 3 repeated 0. So you have to write 0, 0, 0. Even though that you know the value for m is equal to 0, but you have to mention 3 times so that you know that these are repeated roots. And for the quadratic equation m squared plus 5m plus 6 equal to 0, you can factor this or you can use your calculator. So here I get -2 and -3. Another 2 roots here, which are this one are distinct root. It's different root. So it's not repeated. So this one repeated, this one distinct root. So based on this, since that I have 3 here and then 3, 4, 5. So I have 5 roots. Means that the corresponding solution should be 5 also. Y1 until Y5. So I have Y1 until Y5. Okay, now you look at here, the first solution correspond to the root, the first root here, 0. So e to the power of 0x, you get 1. The second solution also correspond to this, m to the power of m equal to 0. So since that is repeated with the y1, so you have to multiply by x. So the answer here will be equal to x after you simplify. And the third one also correspond to the third root here, which is also repeated with the y1 and y2. So you have to multiply by x squared. So the answer here is equal to x squared. Y4 correspond to -2, get e to the power of -2x. And y5 correspond to -3, which is e to the power of -3x. So after you get all these corresponding solutions, so the general solution for this equation is given by this formula, C1 y1 until C5 y5. So the answer is y equal to C1 times y1, which is 1 here. So this one here. And C2 times x, y2, C3 times y3, C4 times y4, and C5 times y5. So this is the general solution for this fifth order linear equation with constant coefficient. Okay, next, this is the another example involve real, distinct, and complex root. So I show you some technique. The rest you have to do exercise, a lot of exercise, because you can see that different technique may be applied for different kind of equation. So here maybe this one for this equation, we will apply different technique of factorization. So let's see, you have this general solution for this equation. This is the fourth order linear differential equation, homogeneous. So you have this equation. So to solve this, starting with the auxiliary equation. So from this equation, fourth derivative, this one replaced by m to the power 4. This one minus 5m squared, because this is the second derivative. And minus 36 only, because this one is no derivative, means that the m here is m to the power of 0. So there is no m here, equal to 0. So this is your polynomial equation of degree 4. Okay, now so I'm using a factorization to find the root m, because based on this I must obtain 4 roots. So your 4 roots can be any types of roots. It can be repeated, can be distinct or complex root. So let's see what happened. So for this, I'm using the factorization by letting the substitution method. Letting the m square equal to u, because this one, actually if you do like this, you can see that your equation turns out to be a quadratic form, u square minus 5u minus 36 equal to 0. So I'm using the substitution u equal to m square, so that I can reduce this fourth degree polynomial to the second degree polynomial. For this one, u square minus 5u minus 36. Then I can able to use calculator or factorization to solve the u. So so I solve the u, I get 9 and -4. So this one is for the value of u. Then I resubstitute u in terms of m square. I get m square equal to 9 for this one. And m square equal to -4 for the second root of second u. Then from each one of these you have to solve because we need to find four roots. Four roots. So m square minus 9, I get m equal to plus minus 3. I get two different roots, 3 and negative 3. And this one, m square equal to negative 4, I get a complex root, which is plus minus 2i. Okay, so I have 1, 2, 3, 4. Okay, total four roots. Okay, two distinct root, one complex root. Okay, so from here, for this, the corresponding solution y1 is equal to e to the power of 3x for my first root 3. And my second root for negative 3, I get my second corresponding solution, e to the power of negative 3x. Okay. And then for the plus minus 2i, according to this form of complex, form alpha plus minus beta I, my alpha equal to 0, my beta equal to 2. So my third solution, y3, will be e to the power of alpha x. Alpha 0, so e to the power of 0 cos beta x. And this one e to the power of 0 sine beta x. So I get y1 until y4. Okay, y3 and y4 represent the complex conjugate root. Okay, so based on this, the general solution will be y equal to c1 y1. So I substitute the y1 plus c2 y2. This is the y2 plus c3 y3. Okay, and then plus c4 y4. Okay, so that's it for this example. Okay, the example of solving the linear homogeneous equation where the roots containing real and complex root. Assalamualaikum and good day, student. So here, I will give another example on how to find the general solution of the homogeneous linear equation. But now this example is, let's say you are given the roots of the auxiliary equation, combination of roots. Okay, for example, you have here 2. You have the root 2. Okay, you have the root 2 here, 2, and then after that 0 and negative 1, and after that the complex root plus minus 2i. Okay, so let's see, after solve you get this kind of the roots here. So what are the corresponding solution for this kind of roots? Okay, so for the first root here, okay, so let's see from here. Okay, we put here for the first root, okay, y1. Okay, so we know that the solution must be in terms of e to the power of mx, right? Okay, so the y1 will be e to the power of 2x. Okay, and for the second solution, okay, since that the second solution and the second root and the first root is repeated. Okay, it's repeated. Okay, so now bear in mind that your y1 cannot duplicate with the y2. So here, since that e to the power of 2x, if you put like this, is repeated with the y1, so you have to multiply that with the x. Okay, so you have the x here. Okay, so we have the y1 is e to the power of 2x, and y2 is x e to the power of 2x. Okay, and for the third solution, okay, y3. Okay, so y3, so we have the 0 here. We have the 0, so e to the power of 0x, so the answer will be equal to 1. So for the third solution, since that the third solution here is not repeated, so you just plug in the value. Okay, m equal to 0. And the fourth solution, y4. Okay, y4 is e to the power of negative x, also not repeated. So we have y1, y2, y3, y4. And then what else? Okay, the last one here is actually complex root. So complex root means that is plus minus, means that involve y5 and y6. Okay, and since that this is complex root, is the complex conjugate. And from here, if you recall back the 4.3 part 1, okay, the complex root must be given in terms of alpha plus minus beta I. So in this case, alpha equal to 0, beta equal to 2. So the y2 will be e to the power of alpha x, 0x, okay, cos beta x, which is 2x, and the y5 will be e to the power of 0x sine beta x, which is sine 2x. Okay, so this is the corresponding solution. Okay, for all correspond to the each roots here, m1 until m6. Okay, so y1 until y6. So make sure you get enough corresponding solution based on the the given roots of the auxiliary equation. Okay, so from here then we can combine everything here y1 until y6 by using the general solution. Okay, so we can combine everything here. Okay, this one. Okay, so all these the general solution, okay, will be y equal to c1 y1 plus c2 y2 plus c3 y3 plus c4 y4 plus c5 y5 until the c6 y6. So your final answer will be, okay, just put everything here, c1 e to the power of 2x, c2 x e to the power of 2x, okay, and we have c3 times 1, okay, times y3, and you have the c4 e to the power of negative x, c5 is cos 2x, and the last one is the c6 sine 2x. Okay, so these are this is the general solution for the given roots there. Okay, so so this based on the given function here. Okay, you can see that the given function here is the y1 until y6.